In this episode, we're looking at permutations that have restrictions. So starting off, if we consider making a word from 3 of the letter A and 2 of the letter B, how many different permutations can be made? So if we list some possible arrangements, we've got A1, A2, B1, A3, B2. We've given subscripts to these A's so that they're distinguishable from each other. But if we were to read all of these words out just using English language, like I know it's not a real word, but abab, we notice that A1, A2, A3, regardless of where they're positioned, they all read the same. So all of these 12 arrangements actually just boil down to one instance, A, then B, then A, then B. So when looking at this, the number of repetitions is going to be 3 factorial for A's and 2 factorial for B's. Thus, the number of different arrangements in choosing 5 letters from 3 A's and 2 B's is going to be 5 factorial, but then we divide by all of these repetitions. So 3 factorial and 2 factorial. We can see in our case, that's going to be 6 times 2, which explains this number up here, 12. It's 3 factorial times 2 factorial. So that would be, in our case, 120 divided by 12, so there's actually only 10 different ways to represent 3 A's and 2 B's. So in general, the number of different ways of arranging n objects made up of groups of indistinguishable objects, that means everything in the first group is indistinguishable from each other. So if they were all of the same letter, or maybe all red counters, then they're going to be indistinguishable. If we give them numbers, then they become distinguishable because we can tell, oh, this red counter has a 1 on it, this red counter has a 2 on it, so those two have to be different. So that's sort of where the indistinguishable comes from. Anyways, if we have n1 in the first group and so on, it's going to be n factorial divided by the number of objects in the first group, so n subscript 1 factorial, n subscript 2, for however many groups you have. Let's say we've got R groups. So it's going to be up to n subscript R factorial. Note, if there are elements of the group which are not duplicated, they can be considered as a group of 1. So you don't need to divide by 1 factorial. That doesn't really tell us anything. So we just omit groups of 1. Example 10. Determine how many different permutations of 7 counters can be made from 4 black and 3 white counters. So we have to choose 7 counters. That's 7 factorial. But 4 of these black counters look exactly the same. 3 of these white counters look exactly the same. So I have to accommodate for that repeat. So that's going to be dividing by 4 factorial, 3 factorial. What that gives us is 7 times 6 times 5 over 3 times 2. So that's cancelling out the 4 factorial that's embedded in the 7 factorial, and that's going to give us a value of 35. Worded question, we want a worded answer, so there are 35 different arrangements that can be made from 4 black and 3 white counters. Okay, so adding on to restrictions of this. So what happens if we say, oh, I need to lock in this position? So for instance, if we have a rowing crew of 4 rowers needing to be selected in order from the first seat to the 4th seat from 8 different candidates. Determine how many different arrangements are possible if there are no restrictions. So just starting off, absolutely no restrictions. It's going to just be NPR is equal to 8P4. We have 8 different rowers and we need to put them in 4 different positions. So that's going to be 8 factorial over 4 factorial, which is 8 times 7 times 6 times 5, which is 1680. So there are 1680 ways of arranging 4 rowers from a group of 8. That would be our sentence solution. In the interest of time, I'm just going to omit that. So for part B, Jason or Chris must row in the first seat. So the number of arrangements there is going to be number of ways. So let's call it number of arrangements is going to be the number of filling seat 1 plus the number of ways of filling the other 3 seats. So that's going to be 2 ways of filling the first seat, and then we had 8 people, but now we only have 7 left because either Chris or Jason must be in the front, and then we're choosing 3 more seats from that. So 2 times 7p3, that's 2 times 210, which gives us 420 different ways of arranging the 4 rowers. If Jason and Chris are in the first seat. So for part C, Jason must be in the crew, but he can row anywhere on the boat. So we have to consider all of the ways that Jason is in the boat. So it could either be Jason's in the first seat, then 7, then 6, then 5 options left, or we could do 7, 6, J, 5, or we could do 7, J, 6, 5, or we could do 7, 6, 5, J. Right, so we're placing Jason around the boat, and then adding up all these possibilities. So it's going to be 4 different ways of finding 7p3, right? 4 different ways of placing the other 3 people. So that's going to be, like we looked at earlier, 210 for 7p3, which means this is going to be 840 different ways of arranging the 4 rowers if Jason must be in the crew of 4. Okay, and then lastly, part D, Jason is not in the crew. So all we're doing there is choosing out of 1 fewer people. So instead of being 8p4, it's 7p4, which is equal to 840. So there are 840 ways of arranging the crew when Jason is not included. Okay, let's look at the word counter. How many number of permutations of the letter are in the word counter? So we have 7 letters. We're arranging them into 7 positions. So this is just going to be 7 factorial, which is equal to 5,040 ways. So there are 5,040 permutations of letters in the word counter. Part B, in how many of these do the letters C and N appear side by side? So we have to consider. We're going to have CN or NC somewhere along this word. So imagine that you get some rope and you tie them together. They're considered as one unit. So there's 2 ways to represent those 2. Then there are 6 ways that things can be arranged. So all we're doing is taking this CN and this NC, and then we're choosing one of them as a letter. So imagine you replace the letter C and N with a joint letter CN. All you're doing then is arranging 6 different letters then. Right, so CN or NC is going to go into one of these points. Then you'd also have O, U, T, E, and R. O, U, T, E, and R. Hey, look, it spells outer. So all of these 6 possibilities, so these 5, and then this joint possibility that's either NC or CN, are going to be placed into these positions randomly. So we've got 2 options for our CN or our NC, and then we have 6 factorial for our block of CN or NC, and then those 5 other letters. So that gives us 2 times 720, which is 1,440 permutations where the letters C and N appear together. Part C. In how many permutations do the letters C and N appear apart? So what we want to do there is take our total number of arrangements that we found in part A and subtract the instances where they're together. So because appearing side by side and appearing apart from each other are the complements of each other, that's what we looked at 2 episodes ago, complements of each other, we can subtract the 1,440 from this 5,040 different ways, and that'll give us the number of ways that C and N appear apart. So it's going to be 5,040, take 1,440 for a total of 3,600 different ways that C and N appear apart. Lastly, we're asked to find the probability of the letters appearing side by side. So instead of subtracting these values, we instead use our probability formula, which is going to be N of A over N of this sample space, which is going to be 1,440 divided by 5,040. So that gives us a probability of 2 out of 7. Okay, we now have two other words to consider, parallel and lines. So we're asked, how many arrangements of the letters of the word lines have the vowels grouped together? So similar process as before, but instead of saying C and N, we're now told the vowels are grouped together. So we have to sort of do a bit more of the grunt work to understand what that means. So vowels are A, E, I, O, and U. So our vowels are going to be I and E, or the other way to order those is E and I. So then instead of having 5 things to choose from, 5 factorial different ways, we're going to have 4 factorial, 4 things to choose from. The I and the E in either iteration, then we'd also have L, N, and S. So we've got 2 ways, and then, not 5 factorial, 4 factorial ways of solving that. So 4 times 3 times 2, which is 24, times 2 is 48. So there's 48 different ways to have the vowels grouped together. To have the vowels separated, again, we just do what we did in the last one, which is take that away from the total ways. So total ways is going to be 5 factorial, which is 120 ways. And then we want to subtract our 48 from that value, which gives us 72 ways in which the vowels are separated. Okay, part C, we're asked, how many arrangements of the letters of the word parallel are possible? Now, I'll give you just a little bit of a moment to have a think. What is this different to than lines and counter? Well, we have repeating letters. So we have 2 A's and we have 3 L's. So this brings us back to this idea up here, the number of ways of arranging n objects with indistinguishable objects. So all those L's and all those A's are indistinguishable. So we have to accommodate for that. So this is going to be 8 factorial, which is my total, but then I divide by 2 factorial different ways to arrange the A's and 3 factorial ways to arrange the L's. So that's our repeating there. So we're going to have 12 different arrangements that are actually all the same. So that gives us 8 times 7 times 6 times 5 times 4 divided by 2, which is 3,360 arrangements. And then lastly, we're asked to determine the probability that in a randomly chosen arrangement of the word parallel, the letters A are together. So we combine our letters A together, but this time we don't have 2 ways of doing that, right? There are identical letters in that group. So there's no distinct internal rearrangements. So all this is going to be is 7 factorial ways to choose the letters. So remember, we've combined A together. So we've got P, R, L, L, E, L, and then choosing the A's together. So 7 different things. But we still have that repeat of the L's. So we got to divide that by 3 factorial. This gives us 7 times 5 times 4 times 3, which is going to give us the number of elements in the event. So this was a probability. So the number of elements here is going to be 7 times 6 times 5 times 4. So that's 30, 210. So yeah, this is 840, right? But then we also need to know what is all of the total number of arrangements. So the total number of arrangements is 8 factorial over 2 factorial, 3 factorial. That's what we looked at in the previous one. So the probability of A is going to be the number of A over the number in the sample space, which in this case is 840 out of 3,360, which is actually a 1 in 4 chance. So there's a 1 in 4 chance that these two A's are going to be together. That is all the examples for today. Thank you very much.